What we're going to look at here in this video is we're going to look at a type of sequence called a geometric sequence. Now this differs from an arithmetic sequence in one key way. If you remember back to arithmetic sequences, they go up by a set amount each time, so you're adding on a constant amount. Geometric sequences go up dependent on a ratio, so they take something and multiply it by the same amount every single time to determine the next term. So that's the type of sequence we're going to look at. But how do we determine what this sequence looks like, and how do we determine what we're multiplying by each time? Well, let's imagine that we generate a sequence, and what we do is we look at the ratio of each of the terms to the term previous to it. So each of the terms to the previous one. So for example, if I look at un plus 2 divided by un plus 1, so the ratio of the n plus 2th term to the n plus 1, and I then look at the ratio of un plus 1 divided by un. If I do this for both of these, what I'd hopefully notice is that they're both the same answer, which we are going to call r. So what that means is the ratio of two terms, any two terms, from the term after to the term before, is going to be the same the whole way along the sequence. This is what we call a geometric sequence. This constant r also has a special definition. This is called the common ratio. So what that means is that's the ratio of the next term to the previous term, regardless of where we are in the sequence. We'll always get that answer. What we could do is if we take un plus 1 divided by un equals r, so if we take it to be at this point here and we manipulate that, what we're able to do is take this divide, stick it across this side and rearrange that so that we get un plus 1 equals r times un. So the next term equals r, our common ratio, times the previous term. So this first order linear recurrence relation, what we can do is give that a general format and say that we can generate the nth term of this using un equals ar to the n minus 1, where similarly to the arithmetic sequence, the a is u1, so it's our first term that's generated within the sequence, and the r is still the common ratio throughout. Now the natural reaction to this is to think to yourself, well, how can I think and know that that is actually true? How do we know that un equals ar to the n minus 1? How do we know that works? Well, what we can do is we can use a technique called proof by induction in order to prove this property itself and show that it actually works for any geometric sequence. Now let's imagine that for a geometric sequence we know that u1 equals a. Now because we know it goes up in a common ratio, what we know then is that u2 is equal to a times r, u3 is equal to a times r squared, u4 is equal to a times r to the power of 3, and each of these takes the format of un equals ar to the n minus 1. So each of them take the format that we are after. So this pattern suggests that. Let's imagine then we look at the first term, n equal to 1, and we look at the general format for it there. What we can say is that u1 equals a times r to the power of 1 minus 1. So that's r to the power of 0, which is simply equal to a. So what we can then say is fine, so it's true for n equal to 1. So it's true for the very first term in our sequence. Now as proof by induction tells us to do, what we then say is that we assume it's true for a generic term. So we assume that it's true for our nth term. So assume it's true for un equals ar to the n minus 1. What we then want to do is look at the next term, so the un plus 1th term. So we have to look at it and see if that format comes up. Well, we know that that's going to be un, our previous term, times the common ratio, because we're going up by that amount every single time. I know that un is given by this, so in this case that's then ar to the n minus 1 times r, and this is going to be to the power of 1. So if I then simplify that, what that means is I get something in the format of ar to the n. Well, that there is exactly the same format as this. The only difference is instead of the nth term, I've got the n plus 1th term, and if I'm on the n plus 1th term, I substitute n plus 1 in here for the n, and I'd end up with the power after there, which is n. So what we can say is fine, it's true for a generic term, it's true for the next term, so therefore it's true for all terms. So it's true for all n. So there you go, we've proven that it works. That's how a geometric sequence looks. That's how it works in terms of progression and how it goes up, and that's our general term for it. We know this is all true. Now we've got to ask ourselves, what kind of questions are we going to need this for? What kind of things are we going to have to calculate with it, and what are we going to have to be able to do with it? Well, a couple of key things that we have to look at is terms. So for what term does this value come up? We have to look at being able to calculate common ratios, and we have to be able to look at using the initial term to do something to other terms as well. So let's look at a couple of examples. Let's imagine I've got a sequence that was 4, 8, 16, etc. What I want to do is find, for the first part, the nth term, so some sort of format for un, and then I want to use that to find the 10th term. So what I mean by un is I could write un equals a r to the n minus 1, job done. But for this, I want to know what a is and I want to know what r is. Well, to get a, we know it's u1. It's the first term, which in this case is 4. Now to get r, your common ratio, we know we've got to take the next term and divide it by the previous term. Now this should work for any pair of terms that are consecutive. So for example, if I focus on the first two, u1 and u2, what I get is I get 8 divided by 4, which is 2. If I were to focus on the next two terms, so 8 and 16, I'd get 16 divided by 8, which again is 2. So from that, I can say that r, my common ratio, is equal to 2. So I can plug all this together and say, fine, so my un equals a, which is 4, times 2 to the power of n minus 1. Now this is the kind of thing where we can manipulate it a little bit. If it wants it in its simplest form, we could, if we really wanted to, write the 4 as 2 squared and have it as 2 squared times 2 to the n minus 1. And because these are the same bases, we can combine the whole thing. Remember, when we're multiplying, we add the powers together. So that's then equal to 2 to the power of n plus 1. So you get two different formats here. A lot of times, this will be sufficient. If it asks for it in its simplest form, and you notice that the number here, the a, can be written as the same base here, or they can both be written in terms of the same base to a set power, you can combine them. To be honest with you, for part B, I'm just going to stick with this first part here. For part B, we want the 10th term. So we know in this case that n is equal to 10. So we want u10 equals 4 times 2 to the power of 10 minus 1. So in this case, it's going to be 4 times 2 to the power of 9. And if we do 4 times 2 to the power of 9, what we're able to say then is fine, u10 is equal to 2048. So there you go, we're able to find the nth term, so some sort of formula for it, and then a set term within the sequence. So that's one application of it and one thing we can do with it. Another thing we might have to do is physically find the geometric sequence itself when we're given a couple of terms. So in this case, we want to find the geometric sequence whose third term is 48 and whose eighth term is 49,152. So a bit of a jump there. What we have to do in this sort of one is set up relationships to find what we know and then use that to solve for the AR for both of them. So in this case, we know that U3 is given by A times R squared, and we know that that's equal to 48. So we know AR squared is equal to 48. We also know U8. So we know that U8 is equal to A times R to the power of 7, which we also know is 49,152. Now, looking at the ratio of consecutive terms, we'd be able to say, this is our common ratio, we can plug it together. But these aren't consecutive. R to the 7 is not the same as R to the power of 2. So it's not just one jump between them, there's a few. But we can still use this to our advantage. because if we were to take the ratio of them and do AR to the 7 divided by AR squared, what I'd know is from that I could calculate R to the power of 5. Similarly to how we'd get rid of a squared, we'd take a square root. Well, for this one, we could take the 5th root. So if we know what AR to the 7 divided by AR squared is, we know that that's equal to R to the 5. We take the 5th root of it, and we can find out what R is, and then use that to find out A. Well, if I do AR to the 7 over AR squared, so 49,152 divided by 48, what I end up getting for that is 1,024. So I know that R to the 5 equals 1,024. So R is equal to the 5th root of that, so the 5th root of 1,024, which in this case is 4. So I know that my common ratio R is equal to 4. What I can now do is substitute this into either of these two equations, and I can find out the A. Let's go for the easier. Let's go for this one here. From this, I know that A times 4 squared is equal to 48. So I know 16A is equal to 48. From that, I know that A is equal to 3. Then I can write my generic term for UN. So from that, I know that UN is equal to AR to the n minus 1. So 3 times R, which is 4 to the n minus 1. So there you go, that's my geometric sequence, who gives me a third term of 48 and an eighth term of 49,152. So there's another application of this type of calculation that we can use. What I'm going to do is I'm going to show you a third one. What I'm going to do is try and answer the question, given the sequence 6, 12, 24, 48, etc., I want to find the value of n such that UN is equal to 49,152. So this time I'm given the sequence, but I want a set term within that sequence. So we have to figure out how to be able to do this. Well, the first things we need to figure out for our UN, as we've done in all the previous examples, is find out what A is and find out what R is. Well, I know that A is equal to my first term U1, which in this case is given by 6, and my R is given by the ratio of two consecutive terms. Pick any two you want, as we showed earlier on. I'm going to stick with 12 divided by 6, which is equal to 2. So I know then that UN, which is equal to 6 times 2 to the power of n minus 1, is going to be given my generic term, and for this one to work, I know that's going to equal 49,152. So first thing I do, I'm going to divide both sides by 6. So I end up getting 2 to the power of n minus 1 equals 49,152 divided by 6. So in that case, it's going to give me 8,192. What I then have to do is solve this. Now my n minus 1 is the power, so that makes it a little bit more complex. But think back to when we did logarithms and exponentials. If I take the logarithms of both sides, I can use the rules of logs to bring the power down and make it a slightly simpler linear equation. So if I take ln of 2 to the power of n minus 1 equal to ln of 8,192, what I can then do is bring that power down to the front, and I know then that n minus 1 times the ln of 2 equals ln of 8,192. Now, you're probably looking at that and thinking, oh, that could be a bit complex. But you've just got to remember, ln of 2 is just a value. ln of 8,192 is just a value. They're both just numbers. Yeah, they've got fancy ln's written in front of them, but they're still values at the end of the day, so treat them like a constant. Divide it across and then solve to find n. So I know that n minus 1 is equal to ln of 8,192 divided by ln of 2. So then to solve for n, what I do is I add 1 to this side. So I do ln of 8,192 divided by ln of 2, add 1. And if I take that and I stick the whole spiel in my calculator, what I end up getting is that n is equal to 14. Nice round number of 14. So what I can say is that U14 equals this value that we want here. So it's the 14th term in our sequence. So we can use it for a variety of applications and a variety of different skills that we need to build on and utilize throughout advanced higher, using different techniques from different levels that we've had before.